Okay, let's just get started. Hopefully it'll behave. Well, we're not going to go into much detail. Difficult about them. The difference between probability sampling methods and with probability sampling methods, everybody or every item in the chance of being selected, while a non-probability sampling method, you're not even sure whether everybody has a chance. So the chance may be 0, but with probability sampling methods, nobody has a 0 chance. Everybody has a chance of being selected. Okay. Now, there are 4 types of non-probability sampling methods that we will look at. The first one is convenience, then quota, purposive, judgmental, snowballing. Here's some feedback. All right, so let's look at the first one, which is convenience sampling. Can you guys hear me?
Yes, ma'am.
Yes, ma'am.
Can you hear the feedback?
Yes, ma'am.
Divas. Okay, so with convenience sampling, just like the name suggests, you do this because it is quick, it's inexpensive, it's casual, and it doesn't require very much effort. Okay, so what happens with this one is that researchers use participants that are readily available. So you're doing it at your own convenience. So maybe you are only able to collect data, let's say after 5, after work, then that is when you collect the data. That is when you sample a population. So it is at your convenience. So you might not have time to do it any other time where you would include other elements of the population. You're just doing it when it is convenient for you. So the name pretty much explains it. It is done at the sampler's convenience. Okay, so again, this is not very reliable because if you're only doing it at 5 o'clock and you want to gather information about the public, the information you get at 5 o'clock might not be the best one. So if it's something about the traffic in town, 5 o'clock, most people are driving home from work. So you would say the traffic in Windhoek is always very high if you make conclusions based on that. So that is convenience sampling. Then the next one, before that, there's some examples besides the one I've mentioned. So do convenience sampling in shopping malls, airports. So you would select people as they pass by, asking them questions. What do you think about this? What do you think about that? And so on. Phone surveys may be used by anyone answering the phone between the hours of 9 a.m. and 5 p.m. So let's say, for example, you have a directory. You're just calling people. Whoever answers and they're willing to take your survey, then they will form part of your sample. Then politicians use convenience sampling to determine the attitudes of those they represent when they report on the number of letters voluntarily sent to them by their constituents. Okay, so this one here, what happens, people are campaigning, they send out various letters, vote for me, is what do you think about my my political stance? And usually people who respond are those who really like you or those who really do not like you. Okay, so it's convenient, or even people who think it's convenient for them to send these back. So it doesn't really give an idea of the population. So it is not very reliable. It's quite biased. Okay, then the next one is the quota sampling. So like I said last time here, you're trying to meet a quota. So whether your quota is part of the population. So let's say, for example, at the mall, throughout the week, you maybe have 1,000 people that come and visit the mall. So what you do is you take a sample of about 100 people, because you say you want a 10% representative, for example. So anybody who's willing to answer your survey, as soon as you have the 100 people, then you're good. You can also do this when your population is divided into portions, for example, males and females. So if I wanted to sample students at NUST, and I know we have a 32% female and 38% male, and I say, okay, I'm gonna sample, somebody asking a question. Okay, so I know that the NUST population is 62% female, 38% male. So when I pick a sample, I just want to make sure that it fits in line with that. So if I'm going to sample 100 people, I will pick 62 females and 38 males. So I'm just meeting the quota. So how I choose them doesn't really matter. The only thing I'm looking at is that the percentage is in line with that of the population. Okay, so this method is similar to that of stratified random sampling, except for the randomizing. So remember what stratified is. The population is divided into groups, and those groups are homogeneous. Okay. But with stratified, we use there's randomizing that is involved, but with quota sampling, it doesn't matter. As long as I get 62 females and 38 males, I can say that my proportions inside my sample is the same as that in the population. So that's pretty much all I care about. And the next one is the purposive or the judgmental sampling method. So I mentioned this one last time as well, where I said this is where you use your judgment in deciding who forms part of the sample or not. So this is in cases, for example, where you are looking at I want to say like highly qualified or a very specific field, for example. So if you're interested in something medical, you're not going to just go and ask people at Vernhill. The people you're going to ask are going to be like medical doctors, and you decide how to choose the medical doctors. So you just say, okay, I want medical doctors, and I'm just going to pick these medical doctors. So you're using your judgment. So it's also sampling that has a purpose. You say, this is what I want out of this. Okay. And snowballing, I also mentioned this last week. And I would say snowballing happens when it is not easy to identify members of the target population, and this is usually because of sensitivity or confidentiality. So if you're doing research on HIV/AIDS, for example, gangs, prostitution, those things where people do not openly state that they are part of the population, Okay, so it's not easy to gather all of them and then put their names in a hat and pick 10 if you want 10. What you do is you identify one, and then you ask them, do you know anybody else that would form part of this population? And then they would refer you to somebody. And then from there, you would go to that person. That person would refer you to maybe 2 other people. And then those 2 people would refer you to another 4 people and so on. Okay, so it's like a snowball. Let me see if this will work. So you start with 1 person, then they refer you to 2 people. Then those 2 people refer you to maybe 2 people. This is another person here, like that. So it's like a snowball. So if you've seen a snowball that is rolling down a mountain, you'll see that it just keeps getting bigger, bigger, and bigger. So there's no probability that is involved in this one. Now, the reason you do snowballing, like I said, is for sensitivity. It's not easy to identify people that are in this population group. So that's basically it on the non-probability sampling methods. Do we have any questions?
No, ma'am.
Okay, is it fine? Are you able to distinguish between these 4 types of sampling?
Yes, ma'am.
Yes, ma'am.
Okay, then probability sampling. The first one is obviously that it is unrepresentative. Okay, so here if you're using it's like judgment, okay. So one of the disadvantages of non-probability sampling methods is that it is unrepresentative. Because like I was saying, if you are picking elements that are to be part of your sample based on your judgment, you obviously have a bias. So sometimes you look at a person, this person will probably give me the answers that I'm looking for, then you select them to be part of your sample. Okay, and then others like convenience, because you can only go to the mall to collect data at 1 o'clock. That represent the mall at that time, or they usually go to the mall at that time. So it is unrepresentative of the target population, and it is not possible to measure the sampling error. Okay, now the reason why we want to know the sampling error is because we want to know how reliable is this data, because I'm sure you've heard on ads, cures 50% of the this is tested on this many people as a 99.9%. They say things like that. Okay, so when you know what the sampling error is, that will tell you how reliable that data source is. So with non-probability sampling, it is unrepresentative. You cannot tell what the sampling error is, so you're not sure how representative of the population that data actually is. Okay, now, excuse me?
Your mic.
Yes, I can barely hear you.
Your mic is cutting, ma'am.
Is it? Okay, I don't know what the problem is. Let's hope it'll get better. Okay, so even though these sampling methods, the non-probability ones, do have disadvantages. The reason why we do them is because they're useful in getting an idea of what is happening in the population. So before you start on a research, you might not even have any idea of, so I'm just going to ask some, get an idea, and then from there you can decide what to do or how to carry your research about. So this is for getting an idea of what is happening, even though it is not representative of the population, and you cannot estimate what the sampling error is. Okay, now there are types of errors that arise when a sample of observation is taken from the population. The first one is sampling errors, and then we have non-sampling errors. Now, sampling errors, these occur because only a sample of the population is investigated instead of the entire population. So I'm sure you can imagine if I was to I wanted to find out what the average age of NUS students is without actually taking the ages of everybody and then working out the mean. Errors come from the population. So every sample has its own, can say outliers maybe. So they push the data to one end or another. So if I sampled you guys, for example, I might find that your average age in this class is higher or even lower than the average age of NUS students. And that is because it's the sample that I picked. Okay, so it is clear that estimates based on different samples will differ from one another. So this means that if I worked out the average age of students in another class that I have, I might get another value for the average age, which is different from what I calculate using your ages. And that again is just because it's a different sample. Even though you all come from the same population, because it's a different sample, it contains different elements, it will also come with its own errors. Okay, then the estimate X is the value estimated from the specific sample of the survey of the corresponding value X that would have been obtained had a complete census been conducted. So you have an estimate. We talked about some of these estimates. We said X bar is the sample mean. We use it to estimate the population mean. We talked about P or P hat, depending on what books you're reading, to estimate the proportion of the population, and so on. And then the sampling error, this is a measure of the variability between the different values of the estimate that would have been obtained from all possible samples of the same size and derived by the same sampling method, and the census value obtained under the same conditions of data collection. So this is basically just comparing how the estimates differ from each other. So you take several samples, all of the same size, you obtain the samples in the same way, and then you measure how much they differ from the population. Somebody has their hand up. Do you have a question?
Ma'am, could you please
Yes.
share your screen?
I am sharing my screen. Can you not see it?
I can't see anything.
Is she the only one who cannot see it?
No, I can see your screen.
Okay. Okay, I am sharing the screen. So I am recording this as well. So if you missed something, I don't know what would have happened or caused your screen to not show, then you can see it in the video. But I also sent you guys the notes.
What page are you on? Or what slide are you on? Sorry.
You can follow. I don't know what page this is. It's 10, page 10, slide 10 of 28.
Thank you.
All right. Okay, then we also have these non-sampling errors. So non-sampling errors may stem from many sources in the various stages of collecting and processing the survey data and may occur equally in a full census. So these are not based on your sample itself, okay? So these, for example, are errors stemming from non-responses. So for example, you give out a survey and you ask people a question. Some people might not feel comfortable answering your question, so they leave it blank. So you're left with, let's say it was an average of something. So your average may be lower or may be higher because you're only working with the data that you have. Okay, then response errors. This is maybe when people misunderstand the questions. They're also unwilling or unable to answer the questions correctly. So maybe the language you used was confusing, the way you worded the questions. Those are all part of non-sampling errors. So sampling errors come from the sample itself. Non-sampling errors, these are not because of the individuals or the elements that form part of the sample, but maybe from the surveying process itself. Then we have one more. Errors in processing. This, for example, when you're entering the data, let's say you ask them, what is your gender, male or female? And then somebody wrote female, but you put male. Okay, so things like that. So when you have a large sample where you have to enter those into a computer, maybe such errors do occur, and then it can actually affect the kind of the kind of information that you get. So sampling errors, these are from the sample itself, because you picked this person, and that one, and because of how you picked them. And then non-sampling, this is the way you ask your questions, the responses people get, whether they understand what you're saying or not, do they give accurate responses, and so on. Okay, in contrast to sampling errors, which can be estimated on the bias of the survey data, non-sampling errors are difficult or even impossible to estimate. Okay, that is true because it's very difficult to tell that you incorrectly entered somebody's gender. Okay, so when you're typing things, unless you go through all the data that you entered to check and make sure that it is correct, you might not even notice that you incorrectly entered something. Okay, so these are difficult, impossible to estimate. So you might not even know that somebody incorrectly answered something. You might not know that somebody didn't understand the question and they just answered it the way they thought it was supposed to be answered instead of actually giving you the correct answer. So such things. So here what we do is instead of trying to estimate the error, like the one mentioned, what we do is try our very best to avoid them. So you're very careful, make sure your participants and you are there any problems? Do you understand what this is saying? If you see somebody struggling with something like that. Okay, before we go, are there any questions or move on? Are there any questions? I hope it's not been cutting and you guys can hear me.
It was cutting a bit, but I think it's understandable.
Okay, so I'm using this new thing here, but we'll see how it goes. Okay, any other questions or any questions before we move on? Okay, so with chapter 1, usually that forms part of the multiple choice questions in your test or your exam. The main thing about chapter 1 is understanding and knowing what each of the types of sampling are. So whether it's probability sampling, you should be distinguished between the and how to distinguish between all of them. Now with chapter 2, we look at sampling distributions. So we know that parameters describe populations. Parameters are almost always unknown. Okay, to estimate the population mean, we compute the sample mean, and there is very little chance that the sample mean and the mean identical. However, we would expect them to be quite close. So remember, we last week we said, why do we sample if the data is not 100% accurate? Okay, so we said we sample so that we get statistics, and then from these statistics we will have an estimation of what is happening in the population. Okay, so the first estimate that we will look at is population mean. So we start with and then we'll look at the proportion, and then after that we look at the standard deviation. Now, in inferential statistics, an important statistical question is how reliable and precise is the sample statistic? So we want to know, is the statistic that we are using really reliable? So remember the difference between the statistics and the parameters. So statistics, we have, for example, X bar. This is the sample mean, and then we use this to approximate mu, which is the population mean. Then we have P, or you'll see it written like this, P hat, and this represents pi, which is the proportion in the population. Okay, we also have S, or S squared. This one we use to represent sigma squared. Okay, so I'm sure you've done standard deviation and the variance last semester or last year, so you know how to calculate the standard deviation or the variance. So these are the three that we will be using to estimate what is happening inside our population. Okay, so the sampling distribution provides the answer to this question. That is this one over here. How reliable, how precise is the data? So we will know with what accuracy we can estimate the population parameter. So it shows the relationship between a sample statistic. So for example, the mean, which is the first one we'll be looking at, and its corresponding population parameter. And then it tells us how a sample statistic varies about its true mean population. Okay, so this, like all other random variables, the sample statistic possesses a random distribution. The probability distribution for X bar is called the sampling distribution of X bar. The sampling distribution of a statistic depends on the distribution of the population, the size of the sample, and the method of selection. That's just background. So with sampling distributions, there are three that we will be looking at. We're looking at the sampling distribution of the mean. That is the one we will start with today. Then next lecture, we'll look at the sampling distribution of the proportion. And then from there, we'll look at the sampling distribution of the variance. So like I was saying, X bar estimates the mu, which is the population mean. P estimates the population proportion, which is pi, and then S squared estimates sigma squared, which is the variance in the population. The point estimates, this is a single value of a statistic taken from a sample and is used to estimate a population parameter. If more than one random sample are taken from the same population, the point estimates derived from those samples will vary. Because of this variation in the sample statistics, we'll have more confidence in estimating a population parameter with an interval instead of a single point estimate. This is basically just saying it's better to estimate the population parameter from a sample instead of just using one entry in your sample. Okay, so we can look at a scenario when we would actually make use of this sampling distribution. For example, you're interested in the mean fill volume of a can of soft drink. The mean fill volume in the population is required to be 300 millimeters because that is what it says on the can. An engineer takes several random samples of cans, each of size N, let's say for example 100, and computes the sample average fill volume. Suppose that there are K such samples, then if the engineer calculates the mean fill volume of each of these K samples, they will now be K sample means. So what that means is on the cans of soft drinks, it says that it is 300 milliliters. So what you do is you take a sample. So you have your population. This is all the cans maybe that are manufactured by the company. Then you take part of them. You are saying here, I'm only going to take 100 out of those, however many you have. Okay, so this is your sample 1. Okay, and then what you do after you have taken your sample, you measure each of them and then you get the average. So this is X bar 1. You get your average. Let's say, for example, your average is 301 milliliters. Then what you do is you pick another sample. This is sample number 2. You take 100. Again, not the same sample. Then you measure the average volume. And let's say here you get 299 milliliters. Okay, and then you keep doing this. Then after that, you take the average of all of these. So you take this average, that one, until you get all of them. So you add them all together and get an average of the averages. So you see all these averages that I have is this one. This is an average of this sample. This is an average of that sample. So you work out the average of the averages, and the average of the averages, you see here I have 301, here I have 299. the average of all the averages that you have, you will find is very close, and it is a very good estimator of the population mean. Okay, so this is basically what I was saying. You take all the individual averages. So here, take the first average, the second one, and then that one over there. Then you add them together, divide by k, because they're k samples. You add the averages, and we say that this is an unbiased estimate of the population mean, because there is very little difference between the average of the averages and the actual average in the population. Do we have any questions? So here, what I just want to do is just actually justify why we do this, or why we say that a sample mean is a good estimate of the population mean. So most of the time, what we will actually be doing is not, like in a test or an exam, is not justifying why you're using the sample mean. Most of the time, if you've seen past papers, we're just doing calculations. So we know that it is a good estimate. Now, can you calculate the probability of that? So here's just to justify why we are actually using that statistic. Then the standard deviation of these k samples is the measure of the sampling error. So over here, this is this one here. This is the sampling error of your averages over there, what the sampling means. And then over here, this should be like this, should be X bar. That one, or you can put it in brackets like that. Okay, so the variance of the means, this is the average deviation of the sample means about its true population. So we just say this is sigma squared over n. Now, if I'm here and I want to get there, all I do is, so this is like the standard deviation. And this one here is your variance. So I'm sure you know that when you square your standard deviation, you get the variance. And if you square this one over here, you'll end up with sigma squared over n. Okay, then a histogram of these k-sample means will be normally distributed. I hope you remember from last semester what it means to be normally distributed. And remember also what a histogram is. So data that is normally distributed has a bell-shaped curve, so it looks something like that. So we say that this is normally distributed. So most of the data will lie in that region, and then the further out you go, the fewer elements or people you will find in that. So you can think of this in the way you think about height. Most people are within an average range. There are very few very short people, and there are very few very tall people. So most of us are somewhere in there. So this is a normal distribution. We see that it is bell-shaped. Then here, this just means that X bar is normally distributed, and then this is the mean. This is the mean. Hope you can see that. and this is the variance. Okay, so when you see something written like that, it just tells you that the random variable is normally distributed. The first number gives you the mean, and then the second one gives you the variance. Okay, so we will be using standard normal tables to estimate our probabilities. I hope you know how to read normal table. I don't know if you can see my table on your screen. Can you see it?
Not yet, ma'am.
Okay. Okay, so over here I have two standard normal distribution tables. So I'm sure you've learned how to read them. I'm not sure if how well you can see the data that is inside the table. Now, depending on what type of table you are given, you should know how to read it. The first one over here gives you the cumulative probabilities. So the shaded area, that is the area that the table gives you. And then the one on the right here is similar, except that it only goes up to 0.5. So it will never go beyond 0.5. So it'll stop just there, like that. Okay, the area that is, so the area will only be up to 0.5. It'll never be more than that. Unlike this one, it passes the 0 mark because right there at the center you have 0 and it goes beyond and it's going to positive infinity. Okay, so usually in a test, there's a diagram that is given on your normal table. So you look at the part that is shaded, and then from there you can read off whatever information you are given. So it doesn't mean the information that you will be reading from the table or the answer that you will give is what is shaded in the table. You may have to calculate it. Now, you know, with a normal, standard normal table, the area is equal to 1. The entire area, half of it is 0.5, the other half is 0.5. So if you know what one part is, you can work out how much the other part is. Okay, so this one here, you should see it in a few seconds. This is also a standard normal table. Takes a long time. Okay, so this one over here, this is also a standard normal table. So when you're given a normal table in your test or exam, just be sure what information your table is giving. Now this one reads data from 0 going to positive infinity. So if, for example, you want to work out, let's say, you want to work out this area over here from this table. Now this table here gives you this data. Now I know that from 0 going that way is 0.5. So if I want the one in red, all I have to do is say 0.5 minus the one in blue, because the one in blue is the one that I read off from the table. Okay, so you just have to look at the picture that is drawn on the table, and then from there you should know what is the area that I'm looking for under the graph. Okay, so if a parent population is normal, that means it has this bell-shaped with a mean mu and a standard deviation sigma. So we write it like this: X is normally distributed with a mean mu and a standard deviation sigma squared. Okay. I don't know if it's my internet that is slow, but I can see that the pages take quite a long time to load. Okay, so if I'm pausing, I think I'm just waiting for the screen to change. Okay, so the parent population, that just means the population from which the sample was collected. So if that population is normal, that means it has a bell-shaped. We write it in this way. So we can write it like that. We say that it is normally distributed. So that tilde sign, this one over here, that means it is normally distributed. And the first number, like I said, is your mean. And then the second number that you will have is your variance. Okay, then the sampling distribution of X bar is also normally distributed. So data that comes out of a normal distribution is also normally distributed. Now the way we write it is a little bit different in that its variance is not just sigma squared. This time it is sigma squared over n. So remember, this is the variance and not sigma over the square root of n. Then any sample mean can be converted into a z-score by following the transformation z is equal to x bar minus mu, and then we divide by the error. Okay, so remember, this is our error. So you take the mean, you subtract the population mean, and then you divide by your error, which is sigma over the square root of n. So today I just want us to go over the questions, because this is how you will be assessed. Everything I've been saying before, like I said, was just to justify why we do what we do, why we take our sample mean to estimate the population mean. We show that it is an unbiased estimation, and what you will actually be required to do is calculate abilities like this one. So I hope you've seen the assignment. There are questions like this in the assignment, so I would expect you to do them in a similar way. The first one, it says, suppose you take a sample of 25 high school students. So you should always take note of the information that you are given. So you take a sample of 25 high school students. So this 25 over here represents your n. So you say n is equal to 5. And you measure their IQ, assuming that IQ is normally distributed. So remember what normally distributed means. It means it has this bell-shaped. Most people are within an average, like in the middle, and then there are a few people with a very low IQ, and a few people with a very high IQ. Okay, and then it is normally distributed with mu equal to 100. I'll just take note of that. Mu is equal to 100. Then sigma is equal to 15. Now it says, what is the probability that your sample's mean IQ will be 105 or greater? So you know what the average IQ is. It's about 100. Now you want to know, now that I've sampled these 25 high school students, what is the probability that their IQ will be 105 or higher? Okay, so first thing you have to do is you have to transform your statistic to a z-score, and then you will read the value from the standard normal table. So here what I'm actually asking you is, what is the probability that x bar is greater than x bar? So this is greater than or equal to our 105 over here. Okay, so the only way we can get an accurate reading of this is if we use our table. So our table doesn't have values like 100. Our table is a standard normal. So what we do is we standardize this 105, and we say that the way to do it is we will say x bar minus, and then we divide this by sigma over the square root of n. So when we do this, we have standardized it, and then we will be able to read that from our table. Okay, so here we're just looking for the probability that, now I put a z instead of an x because I am going to transform this 105 into a z-score. So this is z, this is greater than or equal to, I say 105 minus mu, which is 100. Divide this by sigma. My sigma is 15. Then I divide this by the square root of my sample size, which is 25. So here I'm saying, what is the probability that z is greater than or equal to this 105 minus 100 divided by 15 over the square root of 25 that you just do on your calculator. You will get 1.6666, and it continues like that. Now your normal table reads up to 2 decimal places, so here you round it off to 2 decimal places like that. So we're looking for the probability that z is greater than or equal to 1.67. So let us continue. Okay, so what we want to find from our table is this. So this is normally distributed. Now we say that right here at the center we have 0 and 1.67 will be somewhere here. This is 1.67. And we said we want the probability that z is greater than. Now greater than, if you remember your number line, numbers that are greater are on the right of the number line. So we're looking for this area over here. Then now that you've identified the area that you're looking for, you go to your table and look at the table. Now this table over here does not give me the area that I'm looking for. It gives me this area over here, this one, the area on the left, but I'm looking for this shaded area over here on the right. So what I can do, if this is the only table that I have, is I can read this area here from the table, and then to work out this area, I will just say 1 minus this area that the table gives me. So remember how to read your table. You would say, you go to Z, you're looking for 1.67. So this is 1.6 over there. I hope you can see it. There's 1.6. Then the first number next to 1.6 is the value for 1.60. Then 1.61, 1.62, 1.63, 64, 65, 66, 67. So this is the value over there. So from the table, I am getting 0.9525. That is the value I'm getting from the table. But this value, this is the blue that is shaded over here, but that's not the area that I am looking for. The area I'm looking for is the one that is not shaded in the diagram. So to get the area that is not shaded in the diagram, I will say the probability that Z is greater than or equal to 1.67. This is equal to 1 minus 0.9525. In this, you work it out on your calculator. You get 0.0475. So remember, probability is a number between 0 and 1, and you can always write your probability as a percentage. So this is the same as 4.75%. Now, because this was a word problem, your answer should always be a word problem as well. So let me just go back. The question was, what is the probability that your sample's mean IQ will be 105 or greater? Now, when you're answering this question, what you should do is just take these words, here, you'll say the probability that the sample mean IQ will be 105 or greater is 5%. So you write that at the end. Okay, so the sentence is already given there. All you have to do is extract that part. You start with the probability that the sample mean IQ will be 105 or greater is 4.75% or something like that. So word problems, you answer them in words. Do you have any questions on that? Or are we fine? Would you be able to calculate something like this? Okay, let's do some more examples. So these are questions that I got from past test papers, past exam papers. So these are the kind of questions that you can expect in your test or exam. So you have the exercise. I put it there on the home page, also in the WhatsApp group, so you can follow along with me. We start with number 1. Suppose that the ages of a certain population are normally distributed with population mean 27 and population standard deviation of 12 years First question, find the probability that a randomly selected individual is more than 30 years. So it's always good to write down whatever information you are given. So we are told that it's normally distributed. Okay, we have the mean, the population mean. We're told that mu is equal to 27. And then the standard deviation, sigma, this is equal to 12. My pen is not working now. Okay, that's a 12. Okay, then we have to find the probability that a randomly selected individual is more than 30 years. Okay, so here when you're talking about a random individual, that means it's not a random selected individual. So if it's an individual, this means that your n is equal to 1. Okay, so you have n is equal to 1. And you're looking for the probability that x is greater than or equal is greater than 30. Okay, the value for greater than or equal to and just greater than will be exactly the same, but it's always good to write it the way it's asked in the question. So I want the probability that a randomly selected individual is more than 30 years. So what we do is we standardize. So we will say this is the same as the probability that z is greater than, we said our x bar minus mu divided by sigma over the square root of n. So this is the probability that z is greater than our x bar here. This is the 30 minus mu is 27. And then we divide this by sigma. Our sigma is 12 and n is 1, so the square root of 1 is just 1, so I don't even need to write it. You can show it if you want to, but it doesn't make any difference because when you divide by 1, it doesn't change anything. So here, what I will then have, this is the probability that z, I'll say 30 30 minus 27, then you divide that by 12, you get 0.25. Okay, so now it's always good to draw a diagram so you can figure out what area you're looking on your standard normal, or what area of the standard normal you're looking for. So this is what it looks like because it's normally distributed. Now right here in the middle is 0. That's where 0 always is. Now 0.25 is greater than 0, so it'll be somewhere over here. Now you want z that is greater than 0.25. That means you want this area over here. Okay, so this again, you will have to read it from your table. Let me see. Okay, so our standard normal, the one that we have over here, gives us the cumulative probability. So remember what we are looking for. We are looking for this area over there. So what we will do is we will read the value from the table and then we will subtract that from 1. So the number we're looking for is 0.25. We say the way to do it is you go to your z over there. You have 0.2. That's this row over there. The first one is 0.20, 0.21, 2, 3, 4, and then this is the one that we are looking for. So it is 0.5987. So if you cannot see this clearly, you can download these tables from the internet. They are readily available. Okay, so we said when we read this from the table, we get 0.5987. But what we are looking for is not the shaded table, but it's 1 minus that. So we will probability that Z is greater than 0.25. This is equal to 1 minus 0.598. Okay, then that you work out on your calculator. This is 0.4013, which is the same as 40.13%. Okay, then to answer the question, you write as statement. Because this is a word problem, your final answer must also be in words. So what you will say is the probability that a randomly selected individual is more than 30 years old is 40.13%. So that's how you would answer it. I think this is pretty simple. Do we have any questions on that? Is this clear enough?
Yes, ma'am. Clear.
Is that a yes?
Kinda.
Okay, so I'm going to erase this. Well, let me see. Let me just try and get a new page. Okay, and let's look at the second part of this question. We said if samples of size n is equal to 36 are drawn from the population in the previous exercise, which is A, find the probability that the mean age from one of the samples is less than 30. So it's the same question, except this time, instead of asking for the probability that involves just a single individual, here we're looking at a sample. Okay, so what we do, right? So our mean mu is still equal to 27. Our standard deviation is equal to 12 still. And this time it is equal to for the probability that x is less than 30. Okay, so we cannot read x is less than 30 from our table. So first thing we need to do is standardize it. So to do that, we'll say this is the probability is less than our x bar. This is 30. Mu, which is 27. And then we divide this by sigma, which is 12 over the square root of n, which is 36. So this is a probability that z, here we say 30 minus 27 divided by 12 over the square root of 36. So this is 1.5. Okay, then again, you go back to your table. So 1.5, just wait for the table to come on. Okay, so if you have a table over there, you can also read from yours, and I think it'll go by quicker. Okay, so here, if you have your table, you look for 1.5. Now, because this is just 1.5, that means it is 1.50. So you'll look for first number next to 1.5, and that is 0.9332. That's the value I'm getting from my table. Now remember, you need to know what data your table is giving you. So, okay. Okay, so you want the probability that z is less than 1.5. So remember, 0 is, then 1.5 is somewhere here. Then the probability that z is less than 1.5, less than 1.5 means to the left of 1.5. So this area over there. And this area, you will notice, is the same as the one that you would read from your table. Okay, so the probability. Okay, I don't know what is happening. Okay, so the probability that z is less than 1.5, this is equal to 0.9332. So here I don't need to subtract 1 from, I don't need to subtract 0.9332 from 1, because the area that I'm looking for is the same as the one that is given on the table. Okay, so answering the question B, it said find the probability that the mean average of one sample is less than 30 years old. So you would say the probability that the mean age from one sample is less than 30 years old is 93.32%. 100%. Okay, and that makes sense because the population has an average age of 27. So most people are around that age. So if you want to find out the probability that it is less than 30, 27 is less than 30. So most people are around 27. That means they are less than 30. So there's a very high probability that the mean of that sample is less than 30. Okay, I want us to do just one more before we go. Okay, number 2, we're told that an electronics company manufactures resistors that have a mean resistance of 100 ohms. So you are told that mu is equal to 100 ohms and a standard deviation. So we have sigma is equal to 10. Then the distribution of resistance is normal, so it is normally distributed. So if you are asked to write that symbolically, you would say that x this means normally distributed, and then the first number is mu. Then the second one is your variance, not your standard deviation. So you would square that, and then this is 100. My pen is not working anymore. Okay, so the second number is your variance, not your standard deviation. So we use the standard deviation in the calculations, but when you see it like that, you should be able to read it. It is normally distributed. The first number is your mu, then the second number is your variance. So if you have the variance, to get the standard deviation, all you do is take the square root. Now, the distribution of resistance is normal. Then we have to find the probability that a random sample of n equal to 25 has an average resistance less than 95. So around the average is around 100. So if you sample 25 of them, what is the chance that their average is less than 95? So we're expecting our answer to be low because the average is around 100, and if you sample 25 of them, it should be around 100. So we're looking for the probability that is less than 95. We standardize. X becomes this is less than 100, and then we divide this by sigma, which is 10 over the square root of n, which is 25. Okay, so 25. So this is the probability that z is less than this. You read, will work out on your calculator. 95 minus 100 divided by 10 divided by the square root of 25. Okay, so here you get negative 2.5. Okay, so don't be worried if you get a negative number. It is possible to get negative numbers. So what you do is draw what you are looking for on the table. So we know that this is 0. over there. So negative 2.5 will be somewhere over here. So it's negative 2.5. And we're looking for the area less than negative 2.5. So that means this area over here. Okay, then what you do is you go to your table and then you read it. Okay, so you look for negative 2.5. Now, if I look at my table over here, there is no negative 2.5. So what I can do is read the value of positive 2.5, and because this table is symmetric, the value I get for 2.5, I can reflect it on the other side. So if I read this for 2.5, I get 0.9938. Okay, so what I mean is this. Okay, so looking at the table, you cannot see negative 2.5 on the table. So what you do is you read the value for 2.5, and that is the same as the area of negative 2.5, just on the other side. So here, okay, so we want this area over here, negative 2.5, but our table is giving us this. On the table, it is only giving us this reading of 2.5 like that. Very slow. Okay, so this is the area that my table is giving me, but that's not what I want. I want the area from here going that way. Now the area here, this is negative 2.5. The area from negative 2.5 to infinity is actually the same as the unshaded area over there. So what I do is, if that is the only table I have, I read off the value of 2.5, and then I will say 1 minus the value of 2.5, because this area is the one that I want, but the table is giving me this area. And because the normal distribution is symmetric, this small area over here is the same as that area going that way. So my probability over here, this is going to be 1 minus 0.9938. And this is equal to 0.00. Is it 00? My calculator can only give me fractions. 6, 2. Okay, so that's what we have. And you can see that this is very low, and that makes sense because our population mean is 100, and you are trying to find the probability that a sample will have an average that is much lower than what your population mean is. Okay, so I'll stop here for today. I don't know, are there any questions before we go?
No question. Thank you, ma'am.
Okay. Okay, so I'll try and figure this thing out. Hopefully on Wednesday it will be better. If not, then I will maybe have to record part of it, and then in class we do the other part. As I see, I don't know if it's the Wi-Fi or what is happening, that it is so bad. Even changing between tabs is so slow. Okay, so have a good day. Try the rest of the questions. We'll go over them on Wednesday.
Thank you, ma'am.
Bye.
Thank you. Bye.